Hey guys, so let's do some more calculations with this. The only thing we're going to talk about after this, we're going to talk about the idea of buffers and how we use that. And then we'll move into the information for the lab for today, so for the buffer lab. So using pH to calculate a Ka. So if I have a rice table, and I know that the pH of a 0.1 molar solution of formic acid, HCOOH, 25 degrees is 2.38. I'm going to calculate Ka for formic acid at this temperature. So I know what the pH is. So if I take 10 to the negative pH, that gives me the H3O plus concentration. If I know what the H3O plus concentration is, I can plug that in at equilibrium for this H plus. That's also that HCOO minus, right? And I can do the 0.1 minus that if I really wanted to, and then calculate what that K would be. So the way that we do that, we know that Ka is equal to the H plus times the HCOO minus over the HCOOH. We know that the value that we found was 4.169 times 10 to the minus third. And of course, since that's both of those, that's going to be squared. And we're going to divide that by the 0.1 minus 4.169 times 10 to the minus third, which is the value that you see in the table there. Okay, so I can get a value for this, and that's actually not that hard to do. Okay, I have 4.169 times 10 to the minus third. I square that, I divide that. Sorry, hit the wrong key. 4.169 to the minus third. I square that, I divide that by that 0.0958313 that I calculated there. And that gives me 1.81 times 10 to the minus fourth. Okay, so that's the calculation that we've got there. And we could ignore the contribution from the x and just use the 0.1 to do that calculation, and then you're going to find that your Ka is not particularly different, all right? But it is perfectly okay to do that, right? In which case, this would be equal to 4.169 times 10 to the minus 3. That's going to be squared over 0.1. And let me calculate it just to make everybody happy. So I take that negative 3, I square it, I divide it by 0.1, and I end up with 1.74 times 10 to the minus 4, which is not significantly different, okay? So again, you can always make the assumption that the x is small. You therefore do not have to include it in this calculation right here. That is perfectly fine, okay? So that's how we do pH to Ka. So the method to follow to calculate pH to Ka, you write the chemical equation for the ionization equilibrium, which is what we did up here. So we had our HCOOH, and that gives me an H plus an HCOO minus. I know that that's my R. 0.1 molar here, 0 and 0 there. I know that my change here is negative x. This is a plus x. That's a plus x. My equilibrium is going to be 0.1 minus x. Ignore the x. And of course, the H plus is equal to 10 to the negative 2.38. The HCOO minus is also 10 to the negative 2.38. 2.38. And so what we calculate is then Ka is equal to 10 to the negative 2.38 squared over the 0.1 that we started with. And that's exactly what we've set up here. Now, I didn't actually write that out when I was doing this because it was already here, okay? But that is my process, is to fill out that table so I know exactly what values I'm looking for, right? We can substitute our equilibrium concentrations into the equilibrium constant expression and solve for x. And that's exactly what we've done. Okay, this is no different than we've done previously when we knew those equilibrium concentrations and we wanted to calculate the K. All right. One other example. Let's go ahead and do one more so that I can make sure that you are following what I'm doing. So I have acetic acid, HC2H3O2. That's an acid. It loses a proton. I'm left with C2H3O2 minus. And that is my reaction. My initial concentrations calculate the pH of a 0.3 molar, 0.30 molar. Change, equilibrium. I know that this is 0, this is 0. This is a minus x, that's a plus x, that's a plus x. So 0.30 minus x, I ignore the x. And then this is going to be an x and an x. My x, on the other hand, I want to calculate pH here. So if I want to do that, I need to know what that x is. Do I have enough information to be able to do that? No, I don't, because I don't have a K for this, do I? Now, can I look up a K in the tables that I've given you? Absolutely, I could. Since they asked me for a pH, I know that I would need a Ka to be able to solve. So I can go look up that value. And I see ionization constants of some weak acids on page 10. And if I look in this list, I see acetic acid is 1.8 times 10 to the minus fifth. Oh, we've talked about that before. 1.8 times 10 to the minus fifth is equal to x squared over 0.30. That means that x squared is equal to the 1.8 times 10 to the minus fifth. 0.8 times 10 to the minus fifth times 0.3. That gives me 5.4 times 10 to the minus sixth. I take the square root of that, and that gives me 2.3 times 10 to the minus third. I want pH, so since this is H plus, I need to take the negative log of that answer. And that gives me 2.63. Cool. Awesome. And I've done that. And of course, if this was something that you saw on a test, you would know either that I didn't give you the Ka and you needed to look for it, and please look in your handouts for something like that, or that you can't solve this, okay? Please look before you assume you can't solve, all right? We can also use pH to calculate Kb, all right? The process for doing that is not much different. So we have the pH of a 0.1 molar solution of ammonia, NH3 at 25 degrees. That's 11.13. Calculate Kb. So I have NH3 plus H2O. That gives me an NH4 plus OH minus. That's the reaction that we're talking about. My initial concentrations is 0.10 here. That does not matter. That is 0, that is 0. My change is going to be a negative x there, plus x there, and a plus x there. And I know the pH equals 11.13. So if the pH is 11.13, I can calculate the pOH. That's equal to 14 minus the 11.13. And yes, there is a method to my madness. 14 minus 11.13 gives me a pOH 2.87. 10 to the negative 2.87 is equal to the OH minus concentration. Which gives me an OH minus of 1.35 times 10 to the minus third, which is also the NH4 plus. We assume that this is minus x and that is 0. So my Kb is equal to the NH4 plus 1.35 times 10 to the minus third times itself. So same value, so it's squared over the 0.10. So I can square that value, divide it by 0.1, and that gives me a KB of 1.82 times 10 to the minus fifth. Okay, so I have done exactly the same things that I did previously. The hiccup here comes because I was given a pH and not a pOH. So I need to find a way to find that concentration of OH minus. And again, how I get there is not important. You'll notice that this table says 10 to the negative 14th divided by 10 to the negative 11.13, and that works too. That will get you the same value, okay? So that's our calculations that we will do for that. So now you can see how you get from a pH to a Ka or a Kb, and how you can use that setup to be able to calculate what that pH should be based on the information you've been given. Okay, so hopefully that's everything that you have for that. Like I said, we're going to stop here. There will be more examples, absolutely. I'm going to stop here, and we will move into the conversation about buffers, and then we'll be talking about the lab for today.